Okay, let's get started. So, in the last week, we kind of were almost finished with connected components and traversal, and I want to kind of finish that off and then move on to brute force and the uses of brute force algorithms, which, uh, as I might have told you, can sometimes be surprisingly useful in programming contests. So, here's another interesting problem about connected components. We'll start on that. So here's the problem. We have n vertices in a graph. So for example, 1, 2, ... There's n vertices like this. And we have m black edges of length 1 that have already been connected. So for example, let's say n equals 3, m is equal to 1. Then we have these 3 vertices, 1, 2, and 3. And we have one black edge that has already been connected. Let's say it's this one. Let's label it B for black. And the problem says that every other pair of vertices is connected by a red edge of length 2. The black edge has length 1. Length 1. And every other vertex in this graph, or every other pair of vertices, is connected by a red edge of length 2. So this is connected by a red edge of length 2. This is connected by a red edge of length 2. Fair enough. This problem is from the Google Kickstart round E of 2019. Anyway, so the question is, we have to remove edges so that the graph is still connected and the sum of the edge weights is minimal. Okay, so after we do some experimentation with a few simple graphs, we can kind of start to realize that removing edges is not a particularly fruitful way to think about anything. In fact, when you remove different combinations of edges, first of all, it's very difficult to decide what to remove. And when you remove something, it might have consequences for the graph later on, and then that affects your decision to remove other things and so forth. So removing tends to be very difficult in general, just algorithmically. In contrast, when you want to add things, adding is useful, and adding is fast as well. So we should instead think about adding things to the graph instead of removing them. So let's consider like a graph like this where all the edges of length 1 have been connected. So the graph is going to consist of a number of connected components. So in this case, we just consider 1, 3. 1, 3. And there's a black edge of length 1. So what we want to do is we want to keep the graph connected, right? So how do we connect all of our components together, and how do we ensure that within each component we connect like the least number of 1 edges? That's basically what we need to figure out. So for example, we have this 2 over here, and this is connected, and we haven't decided whether we should remove that edge 2, but we actually have to, because to keep the graph connected, right, we have to add this red edge of 2, but we don't have to add this other edge. This edge that was in our previous graph, we don't need to add in order to keep the graph connected. Make sense? So one way of thinking about this is to start with connected components, right? So if we have a connected component, what do we need to do? Well, we need to essentially make sure everything in the component is connected together by one edge, right? So our connected components are essentially this. We start. I'm going to try and explain this a bit more slowly. The way we start is consider the graph. Let's call it G star, where only black edges are connected. That kind of aligns with our intuition because we know that red edges have a lot of length, and if we can remove a red edge, we definitely should if we can, right? We want to keep the graph connected, but at the same time, we don't particularly want to use the red edges. Okay, so in this case, that would be 1 and 3. 1 and 3. And we also have 2 over here, but there are no black edges in this particular component, right? 2 is kind of connected by red edges in the original graph. But since we're only looking at the black edges, we don't consider it. So to keep the graph connected, we need to add a red edge because we don't we cannot add additional black edges. We can only we're only removing edges, right? So removing edges means that we're from another perspective we are adding red edges or removing black edges, if that makes sense. So we would definitely need for each connected component, we would add a red edge. Because let's understand that edge would be there, would actually be red in the graph because we know it's not black, right? If we have a graph of all of the things that are connected by black edges, this is a black edge of length 1. If we have a graph where only the black edges are connected, and we have 2 things that are not connected, we know that in the original graph, they must be connected by red edges. This means that we need to add a red edge for each connected component to keep it connected to the next part. So the 2 is a separate component from 1 and 3, so we should add a red edge like this to red from 2 to 3. But notice that we don't need to add multiple edges between the same 2 connected components, right? That's just a waste of time. The second thing the second problem we might have in this problem is that we might have a structure like this. For example, 1, 2, 3. This is like a G star, so a graph with only black edges. Don't worry too much if this is a bit quick because the explanation is in the notes, and it's also in the particular Kickstart problem, Kickstart round E 2019. This is the problem 1, Cherry's mesh. So don't worry if this is a bit quick. But the point is that imagine if we had something like this: 1, 2, 3, 4, 5, and we had edges like this. Okay. So we had a pentagon, but all of the diagonals were connected, and all of these edges were black edges. So we want to remove edges so that the graph is still connected, right? So if the black graph is connected, the original graph is definitely connected. So what we can do is we can go through the connected component itself, and for each pair of vertices, we can add an edge. So the way of going through a component that minimizes the number of edges is simply to have a cycle. So we know that if this is an actual component in our graph, when we traverse it, we would traverse something like, I don't know, 1, 3, 5, 4, 2. It could be in any order, right? It could be in any order we would like, but this would be one way of traversing this, and this would be a perfectly fine connected component. The graph would be connected, right? The entire graph would be connected, the entire component would be connected, and we wouldn't have to waste edges on those diagonals. So, 1b, 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 and 1b. So the whole point is that whenever we find a connected component that's not a cycle, a connected component of black edges that isn't a cycle, we can basically just turn it into something that looks like a cycle or a line, right? Oh, sorry. Yeah. So something that looks like a line. And that uses the least number of edges. So, to put this more formally, if we assume that L1 up to Lk are the number of vertices in each connected component of the black graph, i.e. the graph where we only have the graph where only the black edges are connected, then, we need 2k minus 1 red edges, right? Because we have not 2k minus 1 red edges, k minus 1 red edges of length 2, right? So the cost is 2k minus 1. And we also have to correct this particular deficiency whereby we have extra edges in the black parts. So what we do is we simply add we know that if we have something like 1, 2, 3, 4, and 5, we only have 4 edges here. 4 edges. Or if there are k vertices in some, if there are lk vertices in some connected component, we need lk minus 1 edges to keep the component connected, but also have the minimum length, right? Lk minus 1 edges of length 1, so the cost is Lk minus 1. I hope that makes some sense. So let's kind of recap exactly what had happened here. We had some vertices in the graph, so let's draw something like this. 1, 2, 3, 4, and 5. So here's our original graph. So for example, this is an original graph. And we also draw some diagonals like this. Let's say that these are all black edges. All black edges. And we also had, for example, a red edge like this, a red edge of length like this, and like this, red, red, and red. What we would do is construct another graph where we only have the black edges, which in this case is just the pentagon. So we would have something like this: 1, 2, 3, 4, 5. We would have this pentagon with all of the diagonals filled in, and we would have this empty vertex 6, which isn't actually connected to anything by a black edge. Then what we would need to do, to keep the graph connected, we have to connect the two connected components together by a red edge, since they are not connected by a black edge. We know that, right? If they are not connected, or if they're in different connected components, then they cannot be connected by a black edge, so they need a red edge. And furthermore, we need to remove some of these diagonal black edges to make sure that our component has the least number of edges itself. We can connect within each component, we connect the least number of black edges that we can. So the way we do this is we add 2 times k minus 1, where k is 1. Where k is 2 in this case, right? Because there are 2 connected components. K is the number of connected components in our case. Plus L1 plus L2 minus 2, right? L1 minus 1 plus L2 minus 1 is L1 plus L2 minus 2. And L1 and L2 are just the number of vertices in each of the components. So L1 is 5, L2 is 1. 5 plus 1 is 6, minus 2 is 4. So we have 4 plus 2 times 2 minus 1, which is 2. So we get 6. And this is the cost of all of the edges we need to remove. Why is that? So if you'll notice, that's not the cost of the edges we need to remove. That's the minimum cost so that everything is connected, right? Yeah. The cost that we need to remove is obviously the original cost of the entire graph minus the cost needed to keep connected. Okay, so that's this problem basically done. It all boils down to just connected components. We need an algorithm that counts the number of connected components, k, and the number of vertices in each component. And then we can use the formula that we figured out, adding the number of vertices of each connected component, adding the cost of the red edges for connecting the components together, and then, well, we have our formula, and that gives us the cost. So one other thing I haven't really talked about is the time complexity of traversal. I guess I should just quickly talk about it. This should have been covered last week, but I didn't really get time. Time complexity of traversal. So if we have n vertices and m edges, then traversing each vertex or node in the entire graph takes O of n plus m time. This is why I haven't been that concerned about how fast traversal is, because traversal is actually very fast. It's linear in the size of the graph. So our walk algorithm, breadth first search, depth first search, all of these traversal methods are exactly the same, take exactly the same amount of time. They all take linear time. I think that's the last of traversal. We'll now move on to brute force algorithms, which is what I was going to talk about this week before I kind of got sidetracked with this connected component problem. Okay, let's talk about brute force. Brute force. So we've covered applications of sets, maps, and dictionaries. We covered graph traversal. We covered sliding window problems. We've covered a lot of techniques so far. But we kind of skipped over the whole idea of brute force. And I said earlier that brute force algorithms can be bad because they tend to time you out. They tend to be very slow and therefore only allow you to get partial marks on the problem. However, I left out that sometimes brute force is exactly what you need to do. So first of all, sometimes brute force might be able to score full marks. And sometimes we don't know, or at least we can't figure out the best possible algorithm in time. We don't know the best possible algorithm for a problem, and brute force can get us partial marks. So I'm going to go through both scenarios. What is a brute force algorithm? What do we do when we do brute force? So, essentially what we're doing is brute force is all about enumeration. So, enumeration. Okay, what does enumeration mean? All right, enumeration means going through all possibilities. Going through all possibilities. And the basic idea of brute force is that when we go through all possibilities, when we consider all possibilities, and we want to output the best value of something or the worst value of something, we want to find something with a particular constraint, or we basically want to solve some sort of problem. If we consider all possibilities that thing can be, we will have covered the entire space, so we will solve the problem eventually. Right? So solving the problem boils down to just checking all the possibilities. That's great. What does that mean in practice? So often the details that have to be thought out are kind of the mechanics of how you actually enumerate through every possible option. Often it's a for loop. Sometimes it's nested for loops. Sometimes it's using permutations and combinations. So we're going to kind of look at the techniques of brute force and searching permutations and combinations and things like that, and how these things kind of tie in together. Because it's very easy to implement the brute force algorithm if you know how to enumerate through things like sets, how to choose permutations and combinations the right way, basically how to enumerate through the structure. That's the only difficulty of it. If you can do that, you should be able to get a good brute force algorithm. But if you can't, it will be much more difficult. Okay, so let me write down a problem statement for a brute force algorithm. So let's just get started. Here is a brute force problem from the ICPC Divisional Contest of 2019. So ICPC Divisional 2019. Okay, here it is. So it says that Jenny is about to submit her answers to a multiple choice exam. So we have a multiple choice exam. With 5 options, A, B, C, D, or E. Exactly one of which is correct. Jenny has to select exactly one choice for the question that she thinks is the correct answer, and she gets 1 point per problem that she answers correctly. As usual, I'm sure that everyone has taken multiple choice tests in their life. In the last minute of the exam, Jenny has caught a glimpse of the answer key. That is, she saw the correct answer for each question. She does not have enough time to change all her answers to the correct answers, but she can make use of a find and replace feature. Find and replace feature. In other words, she can change all of one answer to any possible other answer. For example, she can change all of her answers that are A's into C's. Or all of her answers that are E's into B's. These are examples. She can change all the answers of one particular category, for example, A, B, C, D, or E, into an answer of another type. Now the question is, given that she has only enough time to do at most one find and replace, what is the maximum number of points Jenny can achieve? Yeah, the maximum number of points she can get. So now it's particularly relevant to state the limits and constraints of this. So n is less than 200,000, and we have 1 second for this problem. 1 second time limit. Okay, how do we solve this problem? So, what do we need to do? First of all, since n is less than 200,000, right, we know that something is a little bit fishy here, right? It means that an algorithm that is even linear time should be okay. Okay, so we're looking for a linear time algorithm, right? Let's assume that the test can contain about 200,000 questions, right? N is the number of questions. And assume that the test questions are given as a single contiguous string, for example, A, C, B, D, E, B, etc., right? Okay, so we're looking for a linear time algorithm, right? An O of n time algorithm. But how can we get an O of n time algorithm? It doesn't really make sense, right? We have to somehow enumerate all of these possible find and replace operations. How are we going to do that? That should take ages. Well, the key is that there are only a few types of find and replace operations. For example, we can change A to B, A into C, A into D, A into E. Similarly, we can change B into C, B into A, B into C, B into D, B into E, and the same with C, D, and E. So we can change E into A, E into B, E into C, E into D. Okay? So how many possible find and replace operations are there? well, there are 5 for each response. So there are 5 times, 4 for each response. 1, 2, 3, 4 for this A. 1, 2, 3, 4 for B, and so forth. So there are 4 times 5 equals 20 find and replace operations. So our algorithm is going to be for the string of questions, right? We keep a copy and we do each of these find and replace operations, right? We replace A with B, A with C, A with D, and so forth. And we count the number of marks that she gets. We assume we have the answer key as well, right? And we check it with the answer key. So each check with the answer key is O of n, but since the number of find and replace operations is constant, it's just 20, the number of approximate steps we're going to take is 200,000 times 20, which is about 4 million operations. And we said earlier, I think this is in workshop 2, that computers can do 50 million operations per second. And this will fit well within the time limit, right? So we can do this. We can do this within 1 second. So what we're going to do now is we're going to try and actually kind of code something that looks like this. All right, let's see how we go. So let me open up my coding IDE and we'll see what happens. Yeah, we'll get coding quite soon. Just opening up my IDE. But let's talk about what we're going to do in the meantime. So we're first going to essentially read the questions and the answer sheet from standard input, or from a file, either one. Then what we're going to do is we're going to replace each of these things and then compare to the answer key. How do we do that, right? Let me set everything up. Yep, that's our Python shell. So I'm going to make a new file, and I'm going to call it findandreplace.py, and we'll just code this up. So let me navigate into that screen. Here we go. Okay, I hope everyone can see that now. Great, let's get started. So first we want to read the questions. So essentially the answers, right? In this case, Jenny's answers. Jenny answers. What I meant by the questions was like Jenny's answers. And we're going to read the answer sheet. Right? And what we're going to do Let's see if we can actually read them in. Just check whether my shell is running. Everything seems to be okay. Okay, we've got it. So now what we're going to do is we're going to do this find and replace operation. So the operations we need to do are AB, AC, AD. This is the easy way to do it. AE, BA, BC, BD, BE, CA, CB, CD, CE, DA, DB, DC, DE, and of course EA, EB, EC, and ED. Right? These are all of the find and replace operations we have to do. So let's make a list of all of this. So operations, and we'll make a list like this. So now that we have that, let's make a function, find and replace. Right? So we have, we're taking some string from the operation. So we're going to replace one character with another, right? So our first character and with our second character, right? And what we're going to do is, and we also need the actual string itself. So we need Jenny's answers here. So what we're going to do is we're going to replace the first character in the operations with the second character in the operations in Jenny's answers. So let's make a new string. So our output is an empty string. What we're going to do is, well, yeah, we're going to go and loop through that string. So for character in Jenny answers, if ch is the first character, output plus equals second character, otherwise the output plus equals the actual character we want. Okay, and we're going to return output. Now what we can do from this is actually compare, we can write a comparison function that will compare this output to the answer sheet. So define marks output answer sheet. So for I in range length of output, if output I answer sheet I, then we just add 1. So count is 0, and we'll just write count plus equals 1, and we'll just return count. Well, actually, let's make this variable name a little bit more descriptive. Marks equals 0, marks plus equals 1, and return marks. Okay, so now we have what we need to actually do the enumeration. So for op in operations, our first character and second character is just op 0 and op 1. And we're essentially going to run each of these. So output is find and replace first char, second char, Jenny's answers. And let's write max marks is 0. So marks is equal to, no, m is marks. Let's not call this marks. Okay, our function is called marks. Okay, I guess we should revert to calling this count. Count. Count, count. So m is marks, output, answer sheet, right? And if m is bigger than max marks is equal to m, and we just print max marks. And that's the end of our problem. So what did we do? First, we had to clearly define what we needed to enumerate. In this case, we had to enumerate the 20 different find and replace operations. We realized that a brute force algorithm was actually tractable simply because there were only 20 operations to enumerate, right? And each operation required us to only go through Jenny's answers once, right? And then actually do a comparison. Each of those only took at most 200,000 operations, so we had, in fact, a linear time algorithm. Okay? So I hope that made sense. And in future, we're kind of going to go through how to do brute force when we have a more complicated problem where our permutations or arrangements or things we have to go through are a little bit more complicated than something simple that's like a list and we're just going through that list. We're going to have multiple nested for loops in our next example, but I'll leave that for next week. Thanks, everyone. I hope the explanation of the connected component problem wasn't too quick. If it was, please check out the problem or the notes. If you want to really, really understand it properly, my explanation may not have been the best. But I assure you, if you ask on Discord, I will provide you with an explanation. But I hope you got the hang of kind of how to construct brute force algorithms, when they might be useful, and how you can implement them quite quickly. Brute force algorithms have a huge advantage in that they're very, very easy to implement once you know what you are going to enumerate through and how you're going to enumerate through it. So in our case, we knew we were going to enumerate through a sequence of like operations where we did one find and replace, and each time we were going to do like a replace type operation. And we could have also done like a string dot replace, but I wanted to just code it manually just so you could see exactly what was needed, and so the time complexity would be totally obvious. Anyway, that's it from me today. I will hopefully see you next week. See you around.